Hello, we are going to talk about our machine learning course project in this video. We chose the polynomial regression as our project topic and try related functions of several Python toolkits on some datasets to explore issues such as underfitting, overfitting, validation, and regularization. Through this, we hope to gain a wider and deeper understanding of this regression method. We will give a brief introduction about the concepts and the algorithms we have used firstly, and then we are going to explain our analysis process with some diagrams generated during the implementation of them. Polynomial regression is a form of regression analysis in which the relationship between the independent variable x and the dependent variable y is modeled as an nth degree polynomial in x. In short, it just fits a nonlinear model to the data. There will be two factors which may influence the fitting result: model capacity and the size of dataset. In polynomial regression, model capacity is usually determined by hyperparameters such as the order d of polynomial. The larger the d, the higher the model capacity. Higher model capacity implies better fit to training, which may cause overfitting. Therefore, it's important to choose a proper degree. Validation is a common method for solving this problem. The idea of validation is to randomly divide the training set into two disjoint subsets. One subset is still called the training set, and the other called the validation set. L1 regularization and L2 regularization can be considered as the penalties as the loss function. The so-called penalty refers to some restrictions on certain parameters in the loss function. The model using L1 regularization is called Lasso regression, and the model using L2 regularization is called ridge regression. As the figures on the right-hand side shown, the optimal solution is where the contour and the L graph intersect for the first time. At the corners, there will be many weights equal to 0, which is why L1 regularization can produce sparse models that can then be used for feature selection. And the coefficient lambda before regularization can control the size of the L graph. The greater the lambda, the smaller the L graph, which can be as small as the black box just beyond the origin, which is the most advantageous value. The function graph of L2 regularization in the two-dimensional plane is a circle. Therefore, the probability of making W1 or W2 equal to 0 when it intersects with L is much smaller, which is why L2 regularization does not have sparsity.
Now it comes to the implementation. We use the polyfit function in numpy to implement unary polynomial regression on datasets. The polyfit function given by numpy is least squares polynomial curve fitting. According to the given m points, it does not require this curve to pass exactly through these points, but an approximate curve. Assume y to be the exact curve. We do curve fitting by minimizing the deviation of the approximate curve from y. The distance is calculated as the sum of the square deviation. This is the implication of least squares. If we set the y as the first equation shown on the screen, the sum of the square deviation can be calculated as the second equation. Then, with a series of partial derivative computations and matrix transformations and simplifications, we can get the coefficient matrix A and the fitting curve finally. We built polynomial regression models using the polyfit function on several single-feature datasets. Here, we just used one example to illustrate our jobs. It is about exploring the relationship between time and exchange rate. Firstly, we explore the impact of size of the dataset on the training error and the generalization error evaluated by the mean squared error, which is an average value calculated using 10 cross-validation mentioned before. We have tried different polynomial degrees, and the picture shown on the screen is a typical example on the whole dataset. The red curve and blue curve represents training error and the generalization error respectively. We can clearly see that when the size is bigger than 200, the errors on training set and test set are closer, which is good for building a model with strong generalization. Therefore, when we sampled from the original dataset to explore the relationship between the model capacity and the training error, we set the sample size to be 200, and the results are as follows. The first diagram shows the test error with increasing of model capacity. Due to the insufficient of data, the green curve is not a smooth saddle pattern. Although it fluctuates, we can probably see that when D is around 40, the model will be more generalizing. Examples of 3 situations of underfitting, proper situation, and overfitting are shown in the next 3 diagrams. So far, we only built models on the single-feature datasets. Then, how about multiple features? A particular feature is a good predictor for the outcome. When the number of features becomes too large, the algorithm starts modeling in intricate relations to estimate the output and ends up overfitting to the particular training data. Next, we will focus on the methods to solve this problem.
Well, things become difficult when the numbers of features is too large. In order to deal with this kind of dataset, we introduce regularization into the regression process. Since polyfit is not efficient to handle datasets with more features, instead we choose sklearn, which is sklearn below, an efficient tool for data mining and data analysis. Lasso, ridge, and elastic net are generated to reduce the overfitting problem by introducing penalty. The model using L1 regularization is called Lasso regression, and the model using L2 regularization is called ridge regression. Elastic net is a middle ground between ridge and Lasso. The regularization term is a simple mix of both regularization methods with a mixed ratio. All of the methods have been packed in sklearn, and we can call the functions strictly. Here we raise an example on wine quality to illustrate our experiment. This dataset is from the website mentioned in source code. Here is the basic information about the dataset. Well, here quality is a target variable, others are the features. The dataset is consistent in data type and there is no missing data. Therefore, we only do standardization in data pre-processing. Here is the histogram of the dataset. When training a model, we need to compute some metrics to measure performance of the model. For regression models, we need to analyze errors, which is root mean squared error, RMSE here. And for subsequent analysis, we need to compare training error and validation error.
tenfold cross validation is employed. Here is how we compute them by coding. Method train score is to print out the RMSE. Method val score is to represent the validation errors. Plot learning curve draws a picture about relationship between RMSE and size of the dataset. First, we do the linear regression. Here's the main process. The first line is training error. Second line is validation error of tenfold cross validation. The third line is the mean of these validation errors. When training error is lower, while validation error is high, it's overfitting. That means the difference between training error and validation error is too obvious large to some extent. The model is overfitting. Here we can see the linear regression is pretty good, and there is no apparently overfitting or underfitting when we do this kind of regression. After that, we do the polynomial regression. We use class polynomial features to transform the training set, apply degree to them. Here we set degree to 2 first, and we get model poly f. X poly is the result after applying the model to the input XR. Here the training error is much smaller than the mean of the validation errors. We can conclude that it is a little bit overfitting. Let's see the returns when degree is 3. Here we can see the training error is about 5 and the mean of the validation errors is over 1.5. It's obvious overfitting. Besides, a learning curve can also be used to detect whether it's overfitting or not. The blue curve represents validation error, while the red curve represents training error. As we can see, the overfitting can be reduced by expanding the amount of data to the model. And a simple way to regularize a polynomial model is to reduce the value of the polynomial degrees. Then we use regularization techniques to eliminate the overfitting problem. First, let's see how it works using ridge regression. When we set alpha, here the training error is 1.6, and the mean of the validation errors is about 1.669. Apparently, the model is proper enough. And here is the performance of applying Lasso regression. We set the alpha to be 0.1, and the training error is about 1.666. The mean of the validation error is 1.67, which means the performance is pretty good. Then we apply elastic net to check the performance. When ratio is equal to 0, it's equivalent to the ridge regression. When ratio is equal to 1, it's a Lasso regression. Apparently, the result, it's good enough. From the results above, a summary comparison of these 3 regularization techniques is that ridge is a good default, and if you want feature selection, Lasso and elastic net is preferable. With regard to elastic net. It prefers over Lasso since Lasso may behave erratically when number of features is greater than training instances, or when several features are strongly correlated. This is all about our project. Thank you for your watching.